Welcome, everybody. It's my pleasure today to introduce Bradley Nelson, who will be telling us about parameterized Vietoris-Rips filtrations via covers.
Thanks, Henry, and thanks for the invitation to talk. I actually like these online seminars. It's nice to keep an eye on what's going on. So I'm glad to be able to be speaking at one. Okay, so to get started, first I'm going to introduce what I'm going to be talking about, and sorry for a lot of text, but I just want to put up front what I want to be talking about. So I'm going to talk about what I call Vietoris-Rips cover complexes. So the idea is that we have a data set, you take a cover of the data set, and if we denote the Vietoris-Rips complex of X at parameter R using this calligraphic R, X, and R, you define this cover complex as the union of the Rips complexes of each of the sets in this cover, right? So we're thinking of building up this thing from smaller Rips complexes. So why would we think of doing this? So one thing is that this is a lot smaller than, or it can be a lot smaller than the standard Vietoris-Rips complex. But also if you look at nerves, right, you can also have all this fine-grained structure within each set in the cover. So there's kind of a trade-off where we want to reduce the size of the complex and use the cover and keep track of some of this fine-grained structure. There's been some work, in this direction in general. So I'd like to particularly point out there's the PhD thesis of Iris Yoon, which looks at a scheme for parallelizing persistent homology computation of Vietoris-Rips complexes using an idea that's very similar to this. But also, the other motivation for me coming at this was just the idea of using the cover U to parameterize things that we already know about the data set. Like if you have a map from your data to some other space, you can kind of think of doing something like parameterized topology using this sort of construction. Yeah, one thing I want to point out is Goody actually has something called a cover complex in it. This looks a lot like a nerve. So this is something a little different. I'm thinking of using the structure of the Vietoris-Rips complexes in each set. Okay. So now it's actually, if you haven't seen this stuff, now I'm going to go back and define some of these things that I just mentioned. So we'll just think of general dissimilarity spaces. I'm going to assume metrics because I want triangle inequality for some of the bounds that I use. But what we'll think of is we have a dissimilarity space, meaning you have a pairwise dissimilarity between points. And we extend this dissimilarity to tuples of points, right? So I think of the maximum or the dissimilarity of this tuple, x squared xk, is the maximum pairwise dissimilarity of any pair in that tuple. Then the Vietoris-Rips complex of X at that parameter R is a simplicial complex where I add every simplex where its dissimilarity is less than or equal to R. And then if I talk about a filtration, this is the nested sequence of complexes. So I'm going to assume this dissimilarity, it has a minimum of 0, right? If I have identical points, and then I can add simplices with larger and larger dissimilarities as I go along the filtration. So some nice things about Vietoris-Rips filtrations, which I think a lot of people will be familiar with, is they're very easy to define. They're easy to construct algorithmically. You can get persistent homological features that capture structure in the sample. And then persistent homology is stable to perturbations of your data set and your metric. So the biggest drawback to this is just the number of simplices in this complex, right? So if I build the Vietoris-Rips complex or filtration where I send this parameter R to infinity, I generally will get n choose k simplices, right? So if I think of, say, fixing the dimension k, because I want to compute homology in a certain dimension, and I sample more and more points, this is going to grow something like into the k, roughly. So that's not really great for computation or for storing things on your computer when you go to higher dimensions.
May I ask a question?
Sure.
Bradley, what is the idea behind defining this, let's say maximum? You can have you may define alternatives, say minimum or some other operators. What is the point?
Oh, right here? Maximum? Why do I define
yes,
maximum?
this maximum, yeah. Can we
Yeah,
define
well,
something else?
oh, sorry. Okay, so there are other constructions you can use. So this is like the Vietoris-Rips construction. But okay, so one reason why the maximum might make sense is when okay, so for me to have a simplex and a simplicial complex, I need to have all the faces of it. And the maximum will essentially ensure, okay, so if I define my Vietoris-Rips complex in this way, this maximum ensures that all the faces will be present for the simplex that I want to add, right? So yeah, again, there are other things you might consider, but this particular definition
Okay, I got it.
works out
Thank you.
well. Yeah. Okay. So Vietoris-Rips filtrations have a lot of nice things from a data analysis perspective, but can be computationally difficult, at least when you do everything brute force and naively. So another idea when you want to, say, find some sort of topological signature of a data set is to produce a cover of the data set and construct a nerve. So a cover is just this collection of open sets of the data, right? And if this is discrete, I might just think of this as an open set is just a collection of points, right? And maybe I choose this so nearby points are in the same open set, but I could do something different. Discrete data you can do all kinds of things. So the nerve of the cover is a simplicial complex. And sorry, there's a typo here. So I think of it as simplicial complex where the vertex set is in correspondence with the sets in my cover. And I have a simplex, so it's U0 to UK. And this is where the typo is. It should be if the, say, the k-way intersection of those sets is non-empty. Not just U0 intersect UK. It should be U0, U1, UK. So in classical topology, there's something called the nerve theorem, which tells us why nerves are nice in particular situations. So we'll ignore the part about X being paracompact because we're going to assume that all the spaces we deal with are, say, fairly nice. But the big thing is if U is what we call a good cover, then the nerve of U is homotopy equivalent to the space X, right? So what does it mean to be a good cover? This means that if I look at any finite intersection of open sets, this is either empty or contractible, right? So, okay, so what's good about nerves? They're pretty straightforward to define and construct algorithmically. They're much smaller than Rips complexes or filtrations. But the drawbacks are when X is this discrete sample, there's only one really good way to get this good cover, which is that you use the same discrete topology as X and you kind of lose all geometric structure that you might have had. There's also a question of how do you choose a cover, right? So you lose geometric structure inside the sets, right? I said something like, well, maybe you want to put points that are nearby each other in the same open set, but that's only one choice that you might make. And the other thing is, at least immediately there's not an obvious way to filter if I want to do something like persistent homology, right? The first thing I would need to do is parameterize the construction of sets in the cover to do some sort of filtration. So there are some drawbacks to using nerves as well, right? But they are computationally nice, and at least in the setting of classical topology, there's this nice result called the nerve theorem. So I've talked a little bit about persistent homology, so I'm just going to briefly review what this is, right? So if we have a filtration, persistent homology tells us something about, well, say, topological features of the filtration, but by this I mean like algebraic features of this filtration, right? So I apply the homology functor to my filtration. I get this sequence of vector spaces, so homology of X at parameter 0, right? There's maps induced by inclusion that send me to the homology of my filtration parameter R. So this gives us what we call a persistence vector space or persistence module. This is classified by its barcode. So each birth, or the barcode is a set of birth-death pairs where each birth parameter indicates that a new homology class is born at that parameter in the filtration. And each death parameter indicates that homology class entered the kernel of one of these induced maps. So in order to compare to persistence vector spaces, we want to talk about interleavings. So I'm going to talk about this in kind of a more general sense. So I'm going to just consider two non-decreasing maps. So not like, let's say like maps that shift by a certain amount, just general non-decreasing maps. So say alpha and beta are non-decreasing maps. And then an alpha beta interleaving between homology of this filtration and homology of this filtration consists of two shift maps. So this is going to send homology at parameter r and x to homology at parameter alpha of r and y. And then this g beta is going to send homology at parameter r and y to homology at parameter beta of r and x. Right? And in order to have an interleaving, we basically want this diagram to compute. Right? So we want to be able to kind of apply these shift maps, and they should interact nicely with these, or they should commute with these maps induced by inclusion in the filtrations. Okay, so now when we introduce interleavings, or maybe I should say, right, so the thing that's nice about interleavings is they allow you to talk about, let's say, how the births and deaths in, say, my top row, so a persistent homology of X, can relate to the births and deaths in the homology in the bottom row, right? So if alpha and beta are essentially maps that just shift the parameter by some fixed constant, so r goes to r plus epsilon, this gives me something I can use to define what's called the interleaving distance and compute interleaving distance between persistence modules. So there are like extensions of the nerve theorem to the setting of persistence. So as we might expect, if the filtration of nerves always satisfies this good cover property, there's a natural extension of the nerve theorem to persistence. And to say more recently, as in a couple of years ago, there's been results on extending the nerve theorem to interleavings, right? So basically the idea is you relax this good cover property to having what we call an epsilon acyclic intersection of sets. And I'll talk about what acyclic means in a little bit. The other thing I want to bring up is just in classical topology, there's this idea of parameterization by a base space that is sometimes useful to study. So the idea would be something like I have a map from X to B. I might have a map from Y to B, right? So B is going to be called my base space. And maybe I have a map F from X to Y that preserves or essentially computes with these maps, right? So in the setting of discrete samples and data analysis, it generally makes sense to work with covers of this base space B and pullbacks. And this is basically, well, this is the motivation for things like the mapper construction in TDA, right? So this is an example of a parameterized method in topological data analysis. And again, I want to bring up Yoon's thesis where she looks at, something basically like this Rips cover complex I'm talking about, but in a specific setting where this cover U is the pullback of a cover of the real line. Okay. So what I want to talk about in this talk is essentially an interleaving relationship between the full Rips complex and this cover complex. And to do this, I'm going to develop an extension, the method of acyclic carriers, which is something, say, classical algebraic topology to the study of interleavings. I just want to mention there's a couple other applications you can use this, say, related applications, which I'm not going to talk about, which are things like stability of these cover complexes or an approximate nerve theorem in this setting, or just basically an alternative result to a variety of geometric stability results. So the reference for a good chunk of this is in my thesis, and I was hoping to get something on archive, but it's not there yet, so it's in preparation. Let's say. Okay, so before I get into like any technical details, and we may go quickly through the technical details, I just want to show some pictures of like things you might do in this setting. So again, so let's just think about pullback covers for a minute. So again, this is kind of the setting I was talking about where I have a map from a space X to Y, where Y is, say, you could think of like projection into a lower dimensional space, right? You form a cover of Y, you pull back the cover up to X. So some reasons why this is useful is, okay, so first of all, you have like curses of dimensionality, and sometimes this can help with that. But you can also use this to incorporate known structure. And maybe some of the examples I'll show, or the example I'll show has a little bit of this in there too. And again, this is basically like mappers, sort of like the zero order approximation to this, right? You essentially look at clusters in the pullback cover. That's what mapper does. Okay, so here's an example, or basically these examples are going to be a flat torus in 4 dimensions with 500 samples on a coil, right? So this is a 2-dimensional projection of that, where you can sort of see that say toroidal structure. So the first cover I'm going to look at is I project onto the first coordinate. I form some cover of this first coordinates projection, and then I pull it back, right? So what you see here is there's a coloring of sets, right? So red is one set, orange is another set, green is another set in this pullback cover. And of course, there's a lot of overlap in this because it's a cover of the data. So this color gradient maybe shows you something like how these covers are changing. Okay, so let's take a look at this persistence diagram. So I actually see basically, well, let's say qualitatively what I would expect when I talk about homology of the torus if I'm looking at dimensions 0 and 1, right? So I see 2 nice robust H1 classes, and I see a single connected component, right? So, you know, doing this construction, I didn't qualitatively lose out on any information, right?
And you just didn't compute H2?
Yeah, yeah.
No, which is fine.
Well, so in this situation, yes, right. This may not, okay. Yeah, I'll just say, so in general, like whether or not you're able to compute H2 in this situation might depend a little bit on the cover. Yeah, I really should put H2 in this. It's
sure. But this is supposed to be like it's an approximation of the actual Rips complex, but it's computational more efficient. So this,
yeah. So basically, what I'll say is there's like an interleaving, at least for some of this, and that interleaving will depend on the properties of the cover, right? Yeah. So here's another example. Oh yeah.
So is this a good cover? Like yeah.
So not really. So this wouldn't even really satisfy what I was talking about with like an epsilon good cover, right? For example, if I look at like, what is this set? So let's focus on like one of the sets in the middle, kind of like one of these bluish sets. So I kind of have like 2 connected components in this set. And each of those connected components sort of has like a ring in it, right? So it's not really what I would call a good cover in any sense. But one of the things with Rips filtrations, right, is if you grow your Rips parameter large enough, everything starts to become contractible, right? So there's like some notion which this might be considered a good cover. But I just want to say there's actually a lot of structure in these open sets, right? Or these pullback sets that I'm using. And this is why I actually see the homology of the torus versus something like, if I just did the nerve of this cover, it would just be like the homology of the line, right? Which has no H1, right? So yeah, there's a lot of structure in these. And so yeah, I shouldn't expect it to be a good cover because this doesn't look anything like the homology of the line, right?
Thank you.
Yeah. So here's another example. Right, so same data set, but now I'm going to look at a pullback of a projection or a cover of a projection into the first 2 coordinates. So this is a flat torus. So essentially the first 2 coordinates, if I project onto those, I get a circle. And then I pull back this cover and I essentially get a cover of the circle. So you'll see there's kind of this color gradient as I go around the torus is the way you see this, right? And if I look at the persistence diagram, the way this manifests itself is that I get a, say, single persistent H1 class, right? So this actually comes from the nerve of that cover. So that's the circle I project onto because I don't have any, say, sets talking to each other across the circle. And then I get a persistent, or let's say persistent but not infinite H1 class, which comes from, let's say, the fibers of this essentially, right? So qualitatively, I still get this like 2H1. But I don't see, but one of these is now this infinite class, right? So here's some other things you might do. So these past two are pullback covers, but you could do something like build a cover based on 20 nearest neighbors of each point. So here I would see, well, because of the way I did this, you essentially see two infinite H1 classes. The scale here is like much smaller, right? So I see like birth only goes up to 0.3 and death only goes up to 0.4 or so. So there's two infinite H1 classes. So again, I see those two things that I would expect, but now they're both infinite. And here's something that hopefully I'll be able to talk about. So this is basically a cover based on a nested landmarking procedure. So this is kind of similar to, so like in the work of Sheehy on sparse Rips filtrations, this is a cover that kind of mimics some of what happens in that, right? So the idea is I build covers where I have like good local information, and then I kind of build these sets that have connect points that are far apart, right? But the goal is to maintain some amount of sparsity, right? So there's not too many points in any one of these sets. Right? And here you'll see that there's, again, two nice, qualitatively what I'm looking for, which is essentially two big H1 generators, two robust H1 generators. Okay, so those are kind of the examples to sort of show, like, I mean, basically this is one of those things where you can do all kinds of things. You can choose covers any way you like, right? And some of what I'd like to understand is, well, depending on the choice of cover you make, how do you relate this to the full construction, right, without the covers? So to get there, I'm going to introduce filtered acyclic carrier theorem, and I'll probably skip all the technical content and come back to it if there's questions. Okay, so first I want to say, so there's this result from classical algebraic topology called the acyclic carrier theorem. Right? And I'll give some definitions, or I'm just going to say what the theorem is, and I'll get some definitions in a bit. Right? But basically it says, so you have a carrier from one chain complex to another. So C and D are chain complexes, and you have some subchain complex of C. You start with a map that goes from the subchain complex to D. And what this says is that if what I'm calling a carrier is acyclic, I can extend this to a full chain map from the full chain complex C to the full chain to the chain complex D, and that this extension is unique up to homotopy. So really the takeaway from this, like ignoring some of these definitions, is, or the fact that I haven't defined what a carrier is yet, is that there's a way to construct maps between chain complexes from some initial data, right? So that's something we'd like to exploit. I just want to say there's like a couple places where you can find introductions to this topic. So like Eilenberg and Steenrod's book has this, maybe more recently, the textbook by Muckries has this. And I'll just say, so like in, say, algebraic topology, this is sort of like fallen out of favor, this approach, more for like acyclic models. But the nice thing about this is it's actually very concrete and algorithmic, in my opinion. Yeah.
Sorry, can I ask a question from the previous slide? Is
This
this
one?
FSR related to C, the carrier?
Sorry? Say that
Is
again.
this FSR at the top related to the carrier C?
So
Because
this
you start with
calligraphic
carrier
C.
and
Yeah, so C, so sorry. So yeah, I should have said, so C star is a chain complex, D star is a chain complex, right? So I can construct chain maps. So a chain map from C star to D star, one chain complex to another. The carrier is something I'm going to need to define, which gives me a way to construct this from initial data, assuming that's acyclic. Did that answer your question?
How is FSR related to this calligraphic C?
So let me define what the calligraphic C is, and maybe it will.
So this is like a map between two chain complex, and then you take a sub-complex chain complex of C star, and any chain map, you say that it can be extended, but what would be the relation between this extension and the initial one, the calligraphic C?
Oh, so yeah, so the calligraphic C, okay, so you can think of it as a map. Well, it's not really a map. It's an association of basis vectors in C, so the chain complex C. to say full subchain complexes of D. So it's kind of like a multi map or something, like multi-value map. That might be like the best explanation, but
Yeah.
I'll give like a definition for this. In the
no, that's all right.
Yeah.
Thank you.
Yeah. Yeah. So, okay. So first I want to, okay. So the goal is to do this in the setting of persistent homology, right? So I'm going to kind of develop this in the setting of persistent homology, and you can kind of turn all this into the classical setting by just saying, I only have one like parameter in my filtration, right? So I'll just talk about like a filtered object in a category of a post set. So what I just think of is that this is essentially a filtration, right? So, but maybe instead of talking about filtrations of topological or say simplicial complexes, I want to talk about filtrations of chain complexes, right? So idea is that I have this collection of objects, right, and they're related by inclusion. And the shift map is basically related to what we saw in interleavings, where we're going to have a non-decreasing map from one post set to another, and an alpha shift map is just needs to agree with the say inclusions, right? Or whatever, yeah, it just needs to agree with the inclusions. So if I have this object XS, I can either send it to XS prime through inclusion, or I can do the shift map to Y and then follow the inclusion in Y. Okay, so so I'll talk about what a filtered carrier is. And again, you can just get the classical version by just taking your post sets and making them just single object post sets. So this carrier, so this is the calligraphic C. I have two chain complexes which are filtered, right? So CS, DT, and this is an assignment of basis vectors in this chain complex. So I have to choose a basis, right, to filtered subcomplexes of D. So if I understand what T is, I'm just going to drop this superscript from C, the calligraphic C. And you could also define things like filtered carriers of cell complexes. So I'm going to primarily talk about chain complexes, but you can think of this in terms of cell complexes as well. So if I I could say take a simplicial complex that's filtered and assign each simplex to a subcell complex of say this other simplicial complex Y. And if you apply the chain functor, this notion of carrier on cell complexes will give you a carrier of chain complexes. And again, you can just take these trivial post sets to get the classical version, right? So I just forget about filtering anything, right? It's just assignment of basis vectors. Okay, so what do we do with carriers? Essentially, carriers carry maps. So if I have a filtered carrier, I have an alpha shift map. So again, this is a shift map that shifts by this alpha parameter or alpha map from S to T. We say that the shift map is carried by C if the image of the map on any basis element is contained in the carrier of that basis element, right? So this carrier is like a much larger thing than just say the image of a map, right? And this has to hold for all basis elements. Okay, so what does it mean for something to be acyclic, right? So a chain complex is acyclic if the reduced homology is 0, right? So what does this mean? This means that, typically in homology, I'll always have, say, something at dimension 0, right? The reduced homology, you get rid of this, right? So everything is 0. But what does this actually mean in the level of chain complexes? This means that the kernel of my k-dimensional boundary is equal to the image of the k+1 dimensional boundary. So all cycles are boundaries is what we would say. And I want to talk about a notion of beta acyclic, or you might see this as epsilon acyclic in some of these things like approximate Hurth theorems. We say something like, let beta be a non-decreasing map from T to T. And if I have a chain complex filtered by T, it's beta acyclic if every cycle has a bound. Sorry, there's another typo. This should be C to the beta T, right? So if I can essentially find a cycle for every, found a boundary for every cycle by increasing my filtration parameter by beta. So if it's beta acyclic, this basically means that the reduced persistent homology of the filtration has no bars that survive a beta shift. That's what this would say. Okay, so now I want to talk about like, what is it? So we talked about what a carrier is. Now I want to talk about what it means for a carrier to be alpha, beta, acyclic. So I'm going to have two filtered chain complexes, and I have a shift map that goes from S to T, that's alpha, and I have a beta shift map that goes from T to T. Right? So that's the image. Or they're non-decreasing maps. So we say the carrier is alpha, beta, acyclic if the image of any basis element is beta acyclic after we've applied the alpha map, right? The alpha shift map. So in a lot of cases, let's say like in the case that I'll consider today, beta is going to be the identity, just meaning like as soon as you apply the shift map, you're already in an acyclic complex. And then I'll just say it's alpha acyclic. And the thing that I'm trying to say here is basically you have this carrier after initial shift alpha, the carrier is beta acyclic. Okay, so this leads me to the statement of this filtered acyclic carrier theorem, right? So I have two filtered chain complexes, and I have a carrier from one to the other. And if this carrier is alpha beta acyclic, and I'm going to assume that I have a strict total order on my posets and an initial object in S, right? So maybe just to give the concrete example, right? So if I think of a Rips filtration, right, my initial object is parameter 0, and the strict total order comes from the strict total order of the real numbers. So again, I'll think of having a subcomplex. So this is going to be a filtered subcomplex of C, and this is generated by a filtered subbasis of C. And I consider some initial map that goes from this subcomplex to D. And we're going to say that this is an alpha, this should be an alpha shift chain map, and this is carried by the carrier. Then I can extend this to a full, I should say like alpha chain map. So this is going to be F, and the shift that you get is actually beta to the K composed with alpha. So you incur some additional penalty from this beta acyclic property.
What's K? Oh, sorry.
Oh, so yeah, so K is going to be the maximal dimension of the chain map. Yeah, so you anticipated that. And the extension is unique up to beta chain homotopy, where beta chain homotopy just means you're homotopic after another shift by beta. Yeah. Okay, so I have a sketch of the proof, but I think we'll skip through this. But basically, this boils down to essentially figuring out when you can get turn a boundary into a cycle, right? And you always have to be shifting things to turn boundary into cycles. So we can come back to this if there are questions, but yeah. So much for a sketch, right? 6 slides of sketch. Okay, so I'll just make some comments on like what this can give us, right? So if we want to compute induced maps on homology in dimension K, we generally need to extend to dimension K+1. So you can kind of control how much penalty you get from this beta term by only extending your map as far as you need to. And as I said, in a variety of cases, like beta is either the identity, meaning like you don't get additional penalties for this beta term, or if you say take enough powers of beta, so compose it with itself enough times, this will be the identity, right? Generally, like, okay, so like why does this happen in practice? It's because often if you think of a chain complex coming from a filtered cell complex, like typically the carrier in the filtered cell complex is going to become tractable at some point, meaning that you don't need to shift to become acyclic anymore. The other thing I want to comment is I had this assumption about, say, strict total ordering. So if you want to do this in multidimensional persistence, you need to have some additional restrictions on like the construction you use to do this sort of thing. So it works okay in ordinary persistent homology. So I'll go, okay, so maybe I'll give the high level summary of this, which is, so the whole thing about this acyclic carrier theorem is you start with an initial map, right? So you start from a map from an initial cell complex or initial chain sub-chain complex. Basically the comment of this slide is you don't even need to start with that. So, oh, I have another typo. So if I have a carrier, which is what I would say proper with respect to the basis of D star. So again, the carrier starts with basis elements of C and it maps them to D. I'll say it's proper with respect to a basis of D if the carrier of each basis element is actually generated by a subbasis of D, right? So not just an arbitrary, say, sub-chain complex, it's actually generated by a subbasis. And if this is the case, what you can do is construct, let's say, augmented chain maps, which preserve the canonical augmentation with essentially no essential data. And the way that you do this is you just send a basis element in C to a basis element in D. And that's going to be your initial data. And you can just choose the basis element you send this to, or basis element of the same dimension. And again, like this sort of construction is going to be unique up to some notion of beta chain homotopy. Okay, so now, like, why did we go through all this work? It's because what I want to get to is like, how do you just get interleavings from some sort of, from carriers, right? So if I have two filtered cell complexes and I have a alpha acyclic carrier from one to the other and a beta acyclic carrier from, okay, so I'll say alpha acyclic carrier from X to Y. I have an beta acyclic carrier from Y to X. And if I can compose these carriers and they'll also be acyclic, which I should say is not actually always the case. Composition of acyclic carriers does not need to be acyclic. Then I can construct an alpha beta interleaving from the persistent homology of X and the persistent homology of Y. So a sketch of this is basically you construct augmentation preserving chain maps and note that they're homotopic to inclusions, which are also augmentation and preserving. Okay. So now I want to talk about how do we apply these tools to these Rips cover complexes. Oh, sorry, I just went back to slide. I was wondering why that's repeated. So what we want to do is we want to compare this Rips, let's say the full Rips, Vietoris-Rips construction and this Vietoris-Rips construction that uses the cover inside. So we have an inclusion that, so basically because we can think of this as the restriction of simplices in the full construction to ones which all live in a single open set in the cover, we only really need to worry about one map below, right? And this is that map F alpha. So I have inclusions everywhere. And basically this is how do I go from my full Rips construction to the construction where I'm restricting things to sets, right? So if I can construct, well, okay, so the question is like, when can I construct this map F alpha? And if I pass to homology, this is going to give an interleaving that is like an identity because of just the plane inclusion map and an alpha, right? So identity alpha interleaving.
So the space in the upper right, it still only has simplices contained in a single cover element.
Yeah, so it's not an include. So this F is
it's not going to be inclusion, right?
Yeah, and it's not necessarily simplicial either, right?
Yeah.
Yeah, because so generally you can have simplices in here that never appear in the discover filtration, right? So how do you deal with this? Yeah. So what I'm going to do is I'm going to focus on these carriers that are generated by witness sets, right? So I define the witness set of, so I'll think of this as a simplex, a K-simplex. This is essentially the set of all points where the distance from a point to every point in the simplex, right? So Y can be any point in my full data set. And the distance from any point Y to every vertex is less than or equal to the, say, parameter at which that simplex appears. And generally, I want to take the union of these things. So I think of the union of all these witness sets over the faces of the carrier, or sorry, the faces of the simplex. I'm going to define a carrier on the let's say on the level of simplicial complexes, so not chain complexes, where I think of this is essentially the maximal subcomplex generated by this vertex set, right? This is sort of the vertex set that witnesses all the faces in the simplex. The other thing I want to talk about is like we want to think about the restriction of the cover. So I have this cover U to these witness sets, right? So I'll just have this U bar, this restriction. What I think of is I take every set in the cover, my big cover, and I intersect it with this, right? I'm just going to think about sets being intersected with that and just consider non-empty intersections. Okay, so all right, so there's basically three regimes for this interleaving, right? Which are defined by these parameters R1, R2, and R3. So let's say is for R less than or equal to R1, alpha is going to be an identity, meaning that the chain complexes are actually, or let's say the homology is actually identical. So they would have identical persistent homology if you only run it up to R1. Then for R less than or equal to R2, you get a shift by, or a multiplicative shift by 2. And then for R less than or equal to R3, you get a multiplicative shift by 3. So all these regimes are determined by properties of the cover. Okay, so what's regime 1? Basically, this is just, so R1 was the bound on regime 1. And I'll say is this is the largest value so that if I have a simplex, there is some set in the cover that contains that simplex, right? So this is essentially saying like, this is when the complexes are actually identical. So basically the proof of this just follows immediately from the fact they're identical. So that one's not quite as interesting, right? Where this becomes a little bit more interesting is when the complexes are not identical. So I'm going to say is R2 is the largest value, so that if let's say a simplex parameter is less than or equal to R2, then if I look at so this isn't the union of the witness sets. This is the witness set for the whole complex intersected with a set in the restriction of the cover to the larger witness set, so the union of the witness sets of all the faces. If that's non-empty, and this, let's say the restriction of the cover to this larger witness set is acyclic, then, oh boy, this is a typo. This should be a 2. I'm sorry. This should be a, then there are identity alpha interleave where alpha goes from R to R, right? And basically the proof of this comes down to triangle inequality, right? So because this is a condition, right, that I impose saying that you need to have some point Y where that is in this set, right? So this is the witness set for the whole simplex in every set in this restricted cover. Basically what you can do is you can use triangle inequality to show that every set in the this restricted nerve, or sorry, restricted cover forms a cone with some point in the intersections. And because it forms a cone, it's contractible. And so it's going to become its homotopy equivalent to the nerve of this cover. And then because I assume that the nerve of this is acyclic, this is acyclic by the nerve theorem. And then regime 3, again, I'm going to use triangle inequality, but now I'm going to lose that idea that I have a point in the witness set for the whole simplex. And I just say, well, we'll just consider the restriction of the nerve to this witness set. And if that nerve is acyclic, then I can get a 3-time multiplicative interleaving, right? So the thing is, again, this is going to come from triangle inequality. So if you're not in metric space, you might be in, these bounds are not generally going to hold, but you're not necessarily going to be able to form a cone, but you can bound the maximum pairwise distance with points in any one of these sets in this restricted cover by 3R. And this is, so if I increase my Rips parameter up to 3R, I'm going to get a simplex here. So again, this is contractible. my assumption was that the nerve was acyclic, and so the carrier will be acyclic, right? The nerve of this restricted cover. Okay, so comment is outside regime 3, you may not have an interleaving anymore, right? So the reason why this can happen is, so basically like the RIPS, so these RIPS complexes always became acyclic at some parameter. And this means that the homology of this RIPS, the RIPS cover complex is going to eventually become the homology of the nerve of the cover, right? So unless the nerve itself is contractible, you wouldn't expect this to agree with the homology of the full RIPS complex, because the whole RIPS complex eventually becomes contractible. And we saw this in some of the examples I showed, right? Where if the nerve of the cover of this torus, if the cover sort of formed this circle, then I see this infinite H1 generator, right? So that was something that we saw in some of those early examples. Okay, so I just want to say a couple of things about like what this might tell you about how to choose covers when you want to do this, right? So again, when you deal with data, you can kind of do whatever you want with a cover, right? But the question is like, how does this really agree with, can you relate this at all to the RIPS complex, right? So what do we learn from our first bound, right? So if I want to maximize this R1 parameter, then I want to include all R nearest neighbors in some set. So I kind of have a budget for like how many nearest neighbors I want to do, right? Because I don't want to form the full RIPS complex. But if I can include all R1 nearest neighbors, then I can include all R1 nearest neighbors, right? That's what this will say. So to maximize R2, I want to ensure that there are witnesses to simplices, right? So what this means is if I have like really sparse regions of my data set, I might need to have sets that are very large, right, to make sure that I get witnesses, right? So at the very least, like I can include the full simplex that I want to construct the map from in a set, and this will ensure that there's a witness to the simplex. So this R2 basically says maybe you need to make your sets really big when things are sparse. And for R3 and also R2, right, there was this condition that the nerve of this restricted cover is acyclic. And what this means is that you want to have sufficient overlap in sets of the cover, right? So in general, I may not be extending to say like beyond a certain dimension, because I'm only computing homology dimension, say 1 or 2. But I want to make sure that there's at least like 2 or 3 way overlap in this situation, right? So every point, let's say sets should always have like 2 or 3 way intersections with other sets. Otherwise, these nerves are not going to be acyclic in the way that I need them to.
And
so
you should probably wrap up as soon as you can, right?
Yeah. Okay. So I'll just say, so like you can take these ideas and basically like come up with an idea that's basically a nested landmarking procedure, right? So I'll say like at this point, this is kind of heuristic, but it looks a lot like the sort of stuff that Banchi did in this paper on sparse RIPS filtrations, where you greedily, obtain a landmark set for your data set, and then kind of use this as a set of landmark points, and then build covers of say certain landmark sets to construct the cover. And actually, I already showed an example of this, but here's one with like a lot more data points where you can sort of sample 4,000 points on the circle and get a nice H1 generator in pretty quickly using this idea. Okay. Yeah, so that's about it. I guess I want to say like, so some of this is still work in progress. And I think like some of the, so I'm very interested in like the idea of like, how does this relate to sparse filtrations? So the difference with sparse filtrations is sparse filtrations generally reweight edges, right, in order to make your interleaving better. Whereas I'm not really considering that, but like the idea of say, kind of introducing sparsity in the filtration, I think is pretty interesting using this. But I'll say like in general, like the use of these covers, I think like, again, you can come up with very general ways to construct covers, and this will generally be application specific. One thing I didn't talk about too much is carriers actually have like a very nice algorithm for this map extension. And I think like developing algorithms based on that might be quite interesting. And again, so this kind of goes back to like why was Yoon looking at something related to this? So that was in a more restricted setting than what I just talked about. But you can think of like one of the nice things that a cover gives you is it gives you a way to parallelize your persistent homology computation across different processes, where I only need to have, let's say, sets talk to other sets if they have a non-trivial intersection. So I think there are some like interesting ways in which these ideas could be used beyond just like understanding the basic interleaving that I showed. So with that, I'm happy to take any questions.
Great. So before we get to questions, please unmute yourself and applaud for the speaker. Hey, you want to go ahead?
Yeah. Sorry.
Sorry, could I go to page 45? Oh, thank you for the fun talk. Yeah, so I'm a little bit confused to the item number 1. What is lowercase r? How do you?
Oh, sorry. Yeah. So what I mean is, yeah, I just mean this in the general sense of like, so there's like our nearest neighbor algorithms where I have a point cloud and I want to find all neighbors within. So yeah, so this lowercase r is just kind of referring to the idea of finding nearest neighbors with some radius threshold. Yeah, so maybe to be more explicit, because I can see why this is confusing now. So essentially, if you include all your, let's say, if R1 is the parameter that you use in an R nearest neighbors query, right, then you guarantee that R1 is at least, or essentially you have chosen R1, right? R1 is essentially the parameter you use in your R nearest neighbors query.
Yeah, I guess.
You want to make this as, yeah.
Right.
So you want to make this as big as possible if you want to like stay in this regime.
Right, but is there? I guess maybe this is where I missed from my current understanding is that the capital R1. How do I get a good sense? Is that the land? Like, how do I get a good sense of capital R1 if I'm giving a data set? Like, is there like a probing process I can find
like how do you choose
R1? Yeah.
Yeah. So in practice, well, okay. So yeah. So if you have a cover of a data set, you can compute what R1 is kind of explicitly, where it's harder to compute what R2 and R3 are explicitly. But you can compute what R1 is explicitly if you give a cover. For choosing it, so if you make R1 too big, you're going to have lots of neighbors, right? And one of the things we're trying to avoid is like the whole reason is we don't generally want to build the full dense Vietoris-Rips filtration, right? So yeah, in practice, I think it's easier to say, well, I have a budget, take like my k nearest neighbors, say, and then compute R1 from that, right? Just to get a sense of what it actually is.
I see. So so I could imagine some sort of, I don't know, binary search of some sort to try to find R1, like capital R1, while the other two are more of, you know the existence, but it's hard to find for R2 and R3, right?
Yeah, like explicitly computing them, right? You kind of have to test, well, you have to test something. Well, you'd have to test some things that might become more expensive than just computing persistent homology of the thing in the first place, right? So that's kind of one of the problems with R2 and R3, at least getting like exact numbers for them, right?
Okay. Yeah, thanks.
Let me go to Hussein next. So Hussein, you have a question?
Yes, thank you. Thank you for your nice talk. So I was wondering, I'm coming from algebraic graph communities. So I was thinking of this terminology carrier means related to circulation in graph signal, edge signal. And the carrier of a function, you can define a function on edge, which is called edge signal. And over there, the carrier means the function which is not zero, the part of the function which is not zero for the graph. So if you restrict to the graph, graph is a simplicial complex. I was wondering where this carrier of map coming. The carrier over there means you consider those part of the function those part of the function which is not zero. For example, in a graph,
specific edge.
Like the support. Yeah.
Yeah. So it sounds like the support on like a specific
yes, like support.
edge.
But you are saying something. Is there any relation? I want to get some intuition about it. Sorry, maybe there's no.
So I'm not familiar with this use of carrier in the setting of graphs. It sounds like there might be a relationship, but it's not obvious to me. Just hearing the definition for the first time.
Because why I'm interested, because the cycle space is related to kata space, so it is completely useful interpretation. Cycle space is the orthogonal complement of kata space in a graph. And so by cut, you mean you have clustering, bottleneck of your graph. Is there something like bottleneck of a simplicial complex? There should be something like that.
Oh, like something like a graph cut for simplicial complexes.
Yes. I mean, yeah. The vector space of cut.
Yeah, I think there's extension. Well, okay, so this isn't something I know tons about, but I believe that there are extensions to graph cut to simplicial complexes, or like min cut or max cut type algorithms. But this is somebody else might know something more than
let me go to another question
Yes.
that's in the chat. So Yuan, if you want to ask your question, please go ahead and unmute yourself. Otherwise, I'll ask it for you. So Yuan, go ahead.
Yeah, I just wondering what's the relation between witness complex. I think they are very related because you are talking about the landmarks also in this setting, right?
Yeah. So okay, so I'm using witness in the same sense as witness complex, but this isn't a witness complex. So what I mean, okay, so witness is basically what I said, right? You want to look at points which are, say, closer to. Okay, so I have like a edge that I'm thinking about, right, which has two vertices in the edge, and then a point witnesses that edge if it's closer to, say, those two vertices than some other things, right? So the use of witness is similar, but the witness complex itself is defined in a different way, where I essentially have a landmark set, and then I look at, let's say, what parameter are the edges witnessed, or like are simplices witnessed at. So so a witness complex is kind of related to a nerve to some extent, but it actually has fewer simplices than the nerve. Right, where you could think of like witnesses kind of do something like, say, there's an intersection, right, between two sets based around landmarks. But I don't know if that answered your question.
Yeah. Thank you.
Okay. Yeah.
Further questions? Otherwise, I maybe have one. Brad, I was wondering if you could go to maybe your first main theorem. So the one prior to the theorem about R1, R2, and R3.
This is like the one on the carriers, or
prior to this. Yeah, the one on the carriers. Yeah, in section 3, I think.
This one?
Yeah. The one with the proof sketch that was 6 slides. Yeah. So
Sorry.
I was just trying to put this in the setting of section 4 once you get to Vietoris-Rips, right? So because I think section 4 is sort of an example of that. Right? Yeah. But what are all the if I want to apply this theorem to the setup of section 4, where I have the actual Rips complex and the Rips complex associated with this cover, what is what? How do I apply this theorem? Okay. Is that what you're doing?
Yeah, so this theorem is like more general than what is needed for the Rips for that particular application. So alpha is the same. So alpha is like this, it's either like identity or like 2-time multiplicative map or 3-time multiplicative map. Beta is the identity in this RIP setting, right? And the reason why is because I kind of only consider the regime where I become contractible in these like subcomplexes. And so, they just become contractible because they either form a code or form a simplex, right?
Meaning that you don't pay this beta to the K penalty, as you were describing. Okay.
Yeah,
But what are C and D and L?
Oh yeah, so C, okay, so C would be like the chain complex associated with the full Rips complex. D would be the chain complex associated with this like cover complex. So S and T are just like the, say, subsets of the real numbers, which are, say, critical values in the filtration.
I see, an L is sort of like an arbitrary subchain.
Yeah, so part of what I said after this is you actually like, if, yeah, so you don't even actually need an L if you have like this, let's say, proper carrier, right? Which, so the nice thing about like kind of defining things on the simplicial complexes themselves is if you use the say chain basis that comes from the say the chain functor on each simplex, then all your carriers are proper in the sense that I said. So basically you don't even need to start with this initial map. Everything is like this augmentation preserving thing.
Gotcha.
So you don't actually even need L, but you could initialize L using any correspondence between a point in, well, actually, so because you have the same vertex set, you could actually just initialize L to be the map on zero simplices that says X to itself, or a point to itself, right? Yeah, so that's a valid chain complex or subchain complex of C, and yeah, that has an image in D. And yeah, and the rest of this is just saying like basically like what you're trying to determine is like, can I bound alpha, right? Because yeah, so I know alpha is generally not just like the identity, right? Typically you might need to make some sort of shift. And so the game is just trying to bound it.
And those are what you do sort of with R1 and R2 and R3 in these different shapes. Yeah.
Yeah, but the beta doesn't come into play in this Rips filtration. Beta kind of comes into play more in like these things like these epsilon acyclic nerve theorems. So yeah, so you can prove like a version of nerve theorem, like these approximate nerve theorems using this sort of technology too.
I see.
Yeah, so actually if you look at those papers, right, like one uses spectral sequences, one uses like this blow up construction, and this is, yeah, so kind of two different approaches. And this is, I mean, you know, everything's the same at some level, right? But this is kind of like another way to maybe think about things, right?
Cool, thanks. That was really helpful. Well, let's end the recorded portion at least here. So thanks very much, Brad, for a fantastic talk. And thanks everybody for the wonderful questions.
Thanks.